All right, ladies and gentlemen, back in the saddle, back to some vodcast, some new material. We're leaving electrostatics behind us, and we're moving to electric current. Okay, static electricity is charges that are basically still, and current electricity are charges that are moving in a conducting path. I'm going to assume that you have some previous experience with circuits, either from the classroom or from the simulation or from previous science classes or just tinkering by yourself with some circuits. So let's get started. On the screen, you see a simple circuit, okay, right here. How it might look on a tabletop. This is a very simple circuit with like a D battery here, some wires, a light bulb, not even in a socket, okay, a simple switch here. And these are the basics. This is the, pretty much the bare minimum you need to light the light bulb. Obviously, you don't even need the switch, okay? The switch is just like a gate. But that's the basics of what you would need. You need a path from the positive end of the battery around to the negative end of the battery. Notice that I connect into the thread right here, okay, the thread of the light bulb, but I come out the tip, okay? I can't go thread to thread like that. That's not gonna make the light bulb light up. All right, on the right you see what's called a circuit diagram, okay? This is a cleaned up version of an electric circuit, okay? And we typically use a circuit diagram because it's easier to read. So notice that we put nice squared corners on the circuit, even though the wires don't actually look that way, right? They may be curved, okay? And we also have some symbols. So you see the symbol for a battery, okay? The long end is the positive end and the short end is the negative end. Okay, you can also stack batteries on top of each other. You might draw that like this with wires coming out, right? That would be two batteries right there, okay? Here's the light bulb symbol. Here's the switch symbol, okay? And then the only other one you might need to add, okay, that you see very often is what's called just your basic resistor, okay? And that looks like this. I'm gonna carve it out right here, okay? And a resistor is just an electrical component that we use to control the amount of electricity flowing in the wire. Sometimes you need a certain amount. So that's the symbol for a resistor. Okay, one of the first skills in this unit that you should be able to do is to draw a circuit diagram from an actual drawing of a circuit like I've done here, okay, or vice versa, right? If I give you a circuit diagram, you can make an actual drawing or actually build that circuit. So the first thing you need to be able to do is to recognize the symbols for a battery, for a switch, for a resistor, for a light bulb, so that you can draw a circuit diagram appropriately. Okay, from your previous experience with circuits or with playing around with some circuits in the lab, you notice several things. Okay, one is that in the simulation, okay, if you saw that, you should have noticed the direction flow of charges. Okay, the charges that are free to move in a conductor, right, are electrons, and opposites attract. So the electrons are going to come out of the negative end of the battery and flow around toward the positive end of the battery. Okay, but one of the things you should have noticed is that they move very slowly, right? In that simulation, the charges are moving very slowly, which seems contradictory to our experience, right? When you flip a switch, the light is there instantaneously, it's on, right? So there's some disconnect there between the velocity of the charges, right, how fast they're going in the wires, and how quickly the light bulb turns on, okay? And that has to do with the fact that even though the charges move slowly, okay, the so-called marching orders, right, the order that the charges feel to start moving, which is the electrical pressure from the battery, okay, that electrical pressure is known as the electric field. And it's the electric field that travels at the speed of light through the wires, okay? It's not the charges themselves, big misconception, right? Not the charges themselves, they move quite slowly, but the electric field travels quickly through the wires. Okay, you see a few terms here that I've mentioned. The drift velocity, okay, is how fast the electrons move. Okay, I use that symbol there for electrons, how fast electrons move through wire, okay? And it's really slow, okay? It's about 1 meter an hour, okay? Really slow, a meter an hour, right? It's like a list over a yard an hour. That's super slow, okay? And yet, when we flip the switch, the light turns on instantly. And that's because the electric field, okay, which I'm going to put in parentheses here, the marching orders, okay, telling the electrons to move. Okay, telling the electrons to move. That's what travels at the speed of light. Okay, travels at speed of light. Okay, so it's the electric field that travels so fast, right? Okay, it's like, imagine a line of people, okay, lined up, and you're giving them marching orders like you would in a military formation. Okay, when the sergeant tells them to gives them the order, all of them start moving at the same time, right? In other words, the message, the marching orders, travel very quickly, even though the soldiers themselves are moving relatively slowly compared to the marching order, right, which would be traveling at the speed of sound from a person's mouth. So it's the same thing here. The electric field tells the charges to move, and that's at the speed of light, but the charges themselves are moving quite slowly. All right, we have one more term to cover here, which is called the conventional current. Okay. Turns out that, as you probably know, electrons are really hard to see. And if you look inside the wires of the microscope, you're not going to see the charges moving, right? The charges moving in the simulation that you did in class, that was just as pretend, right? We now know, okay, that it is in fact electrons that move through the wire, and they go from the negative end to the positive end. But when scientists first started studying circuits 200 years ago, they didn't know whether the charges were positive or negative, and so they just assumed that the charges were positive. So for the first 100 years or so of electric current study, we assumed that the charge was positive. Okay, and so we still this is sort of a leftover idea, but it's called conventional current. Okay, and I'm going to write it this way: conventional current is the way positive charges would flow. Okay, the way positive charges flow. Okay, and obviously they go from the positive end to the negative end. So what we need to do here for conventional, right, what you see here on the screen is actual flow of electrons going from the negative end to the positive end. But we can actually look at a circuit, okay, oppositely, and we can imagine that the charges are actually positive, right? If it were the positive charges that were moving, they'd be moving this way, right? And so this is called conventional flow. All right. It turns out that when you study circuits, it doesn't really matter whether you assume the charges to be positive or negative, as long as you're consistent. So you're going to see this a lot in textbooks. Okay, even though we now know it's the negative charges moving from the negative end of the battery to the positive end, we still have this leftover idea from earlier called conventional flow, which is imagining that the charges are positive. So often we'll look at a circuit as if there were positive charges flowing. All right, so that's another term and idea you need to be familiar with. Okay, let's take a closer look at what some of the components of a circuit do. Okay, let's go to the next screen here. I've typed a few things out. Okay, the battery is basically the pump. Okay, it's the pump and energy source. Little pen malfunction there. Okay, the battery is the pump and the energy source. Okay, and we measure how much of that it's bringing to the source by measuring the volts. Okay. All right. Of course, we have a pathway. Those are the conducting path, right? Usually made of copper. Okay. Now, conductors have relatively little resistance, but they do have some resistance. Okay. Wires do have some resistance, but most of the resistance in the circuit comes from the thing that's using the energy. In this case, the light bulb, right? But it could be the motor, the heater, whatever you have plugged in, TV, phone. All right. And that's going to have a lot of resistance, okay, a lot of resistance. And then finally we have the charges themselves, right, the electrons, okay, moving through the wires, and those are the energy carriers, okay, they are the things that are carrying the energy from the battery to the load. Okay, and the flow of these charges is called current. All right, and it turns out that these three quantities, okay, I suppose I should write up here voltage, okay, voltage. All right, the voltage of the battery, the resistance in the wires, and the load, primarily the load, and the current, okay, those three quantities, those are the three quantities that are very important in measuring how a circuit behaves. So let's see how those three are related. we actually get to thank a fellow named Ohm, okay, hence Ohm's law. He's the guy that figured out the relationship between these three. Before we get to Ohm's law, I should quickly define how, or I should clarify how we define current. Okay, first of all, kind of strange, but current is going to be the letter I, okay, the letter I, and it's basically like how much charge is passing by you in a certain amount of time, right? So charge Q and time seconds. So if you look at the units here, right, charge is measured in coulombs, okay, coulombs, and times measures in seconds. So that's coulombs per second, but we call that an amp. Okay, you've heard of an amp, right? So 1 amp, right, 1A equals 1 coulomb per second. A dump truck, right, coulomb is a dump truck of charges. 1 dump truck of electrons passing by every second. That's a lot of charge, a lot of current. That's 1 amp. Okay, so here's actually an equation that we'll use to some extent right here. Okay, current. All right, and that leads us now to Ohm's law. Let's go to the next page. All right, so what Ohm did is he got a bunch of different batteries, right, and basically got a bunch of different voltages. Okay, a bunch of different sized batteries. Got himself a data table going here. Okay, had a bunch of different voltages, and then measured the current. Right, how bright was the light bulb, basically, because the more current there is, the brighter the light bulb was. Okay, and what he found was a linear relationship. Okay, when he graphed them on a graph, he found this. Okay, and what that means is that current and voltage are proportional to each other. All right, I could write that like this. Okay, remember this is a straight line, right? Y equals mx. Okay, algebra class, graph for a straight line. Except in this case, the current, okay, and the voltage are proportional. And it turns out that they're proportional in the following way. Okay, just like that. I sort of flipped it around. But that right there is Ohm's law, okay, and it tells you that if you double the current, the voltage must have doubled. If you double the voltage, you double the current. You triple the voltage, you triple the current. Okay, and that's Ohm's law, and that's what we're going to use in class next time.